This is Stats 2, question 13 from 2012. It's also question 4 from the Step 2 Stats support module. It's about a Poisson distribution. We've got this integral to start with, so at some point we are going to be using this, I'm sure. Poisson distribution where the mean is k times the area of a given region. Now, the region in the first instance is a circle radius y. So, of course, the area of that is pi y squared. Times it by k, and we end up with this x to the po of lambda, lambda being k times pi y squared. And of course, we're just looking for the probability that x equals 0, which of course is just going to be what happens when you do e to the minus lambda times lambda to the n, where n is 0, over n factorial, and all this goes away, and you just end up with this here. And that'll be that. The random variable y denotes the distance between a randomly chosen point in the region. Now, the region doesn't necessarily mean a circle. It just means the region. So let's just draw a big region, and let's put a random point down in it. And we want to know the probability that there is a supermarket somewhere in this region that is closer to our point than y. So if we put a supermarket exactly y away, to be closer than y, we just need to be somewhere within this circle around our randomly chosen point. And what's the probability of having a supermarket within this circle? Well, it's 1 minus the probability of not having a supermarket in that circle, which we worked out in the first part here. So we're just going to do 1 minus this, and we'll have our answer to that bit. Good. Hence, show the probability density function is this. Now, when we're looking at this, we can clearly, I hope, all see that this is just this differentiated. So you could just say, well, okay, the probability density function is just this differentiated, and I'll immediately get this. If you just want to know where that comes from, if you take some random probability density function like this, of course, the probability of your function being less than x1, if you just have a random function of x, is the integral of f of x between x1 and 0. If you just differentiate both sides, you get the derivative of this thing here is f of x. So, of course, if we derive this, we'll just end up with f of y. As I said, this is in the FS2 book if you're doing Pearson Excel. You just have this system where the CDF, which is this thing here, a cumulative density function, and the PDF, which is what they asked for, is related by this integral differentiating idea because one is the area and one is the curve. So yeah, just differentiate and we get this here. Find e of y and variance of y. Now, of course, e of y is what is the integral, usually between minus infinity and infinity, of y times the function, the PDF function that we had before. Now, I'm only going from 0 because, of course, y is greater or equal to 0. And, of course, because this was provided to us, so I feel like I need to use this. So that's the second reason I did that as well. Now, it seems pretty logical to multiply this out and put a y squared here. Not actually the thing to do. Because, of course, to make this object, we just differentiated. So we know that this is an integrable object. And, of course, that means we could maybe just do integral by parts on these two things. We can integrate this one, leave this one alone in the first bit, and then we can integrate this one and differentiate this down to a 1, which is fantastic because then this looks a lot like this thing here, just with a wrong thing up here, which I can fix later. Now, this is interesting here. Obviously, the two minuses cancel. We can multiply this in. This is interesting here because when you put in 0, clearly you get 0. When you put in infinity, you get minus infinity times e to the minus infinity is 0. So it's infinity times 0. So what does it go to? Well, the mark scheme just says you're allowed to say that it goes to 0. To prove that, you want to be doing L'Hopital's rule. But I can only assume, since the mark scheme doesn't talk you through that L'Hopital's rule isn't part of the required step 2 thing. I didn't actually look it up, but I'm just making that assumption. If you do want to see L'Hopital's rule done, you can learn it in the FP1 book, I believe. I'm pretty certain it's FP1 for Pearson Excel, maybe FP2, but I think it's FP1. There are some very fantastic videos if you literally just Google search up, x e to the minus x as x tends to infinity. You'll find results of people doing L'Hopital's rule and showing that it does go to 0. So this whole thing is going to go to 0. This is interesting over here, so let's deal with this. We can make a substitution to make this look exactly like this. So the substitution I made was this, because of course this will cancel out the k pi when I square both sides, and it will also introduce an over 2, which is what I need here. So, and of course, when we differentiate it, we're just going to end up with this, which isn't really going to matter. I'm just going to throw it in there. So I replace the dy, throw that out the outside, because when you square this, you get exactly this. The k pi cancels, and you end up with exactly what they wanted you to get here. So we know this is equal to root a half pi. And of course, the 2 1 over root 2s will become a half. The pi's will cancel because one's on the top, and you'll just get a root k on the bottom, and that will be our e of y. And then variance of y is, of course, e of y squared minus e of y all squared is our rule. So this one here, well, that's just this squared, which is 1 over 4k. This thing here is very similar to what we just did with e of y, except you put a y squared there for e of y squared. So just a y squared goes in the front there. And then we have to figure out how to integrate this, which again isn't too bad. We're going to do integral by parts again by just treating this as one of the objects and integrating it immediately, leaving this alone, and then differentiating this for a 2y, and then having this integral here again. The 2 minuses already cancel. We saw that last time to make a plus. This, of course, is 1 over 4k. And now here, this is just immediately integrable because you've got a y here and a y squared there. So I think this just integrates to 1 over k pi we're going to need at the front, I think. And that's about it, with a minus sign, I guess, as well, actually. To cancel out this minus the 2y just is fine. And we already discussed it. Again, so for this one here, L'Hopital's, you have to do the hospital. It works. I think you have to do it twice because you have to do it once to get down to 2y with this thing. And then you're in the situation you were before. So you just do it again and you show that it will also go to 0. Again, the mark scheme just says you should claim that it goes to 0. So maybe it's one that's worth knowing, just goes to 0 unless they very specifically say that you have to show it. In this case, you clearly didn't. Although this was back in 2012, so maybe things have changed since then. Apologies that I can't be more clear about which one that is. Anyway, when you put in infinity, you get here, you get e to the minus, you get 0. And then when you put in 0, you get 1 here, so you get a minus this, which is a plus that. And then, of course, times this by 4 over 4, this by pi over pi. And we'll end up with the thing that was required. Thanks for watching.